tell me what you were trying to do. No,
The dental said I was going to do a free body diagram of A and B.
good idea. So let's do a free body diagram of A and B. So for A, what are the forces?
We have the tension, we have weight, normal, and friction.
Let's do B. So the weight, and here's the tension. Of course, we know that the two tensions are going to be equal in magnitude. So what's next? If you want a final velocity, is the work in your theorem good for that or not? Did you say, Josh?
Yeah, you can
Yeah.
just do the sum of the works, because you can take the component of the weight along the ramp, and you can take the,
So we can say T final minus T initial is equal to W net. So you can look at the displacement of 2 meters and ask how much work is done by the forces. So what kind of system are we going to use here? Because you see, you can use A, then B, or you could use A plus B. What's better? Why is A plus B better?
well, because you have the pin in motion and the connect along the rope, so it would just simplify your equations a little bit.
What is the force that goes away when you do A plus B?
Tension.
The tension, yes. Because if you look at A alone, what are the forces doing work on when A is moving? It's going to be the weight, the tension, the friction force. Does the normal do any work?
No.
Because it's perpendicular to the displacement. But you have to take into account the work done by the tension. But now if you look at B, the net work done on B is going to be the work due to the tension and the work due to the weight. Now, what can you say about the work done by TB and the work done by TA?
They're not the same?
They're not the same, that's true, but they're very close to being the same.
Is it just a cosine?
It's not a cosine,
They're opposite.
they're opposite. So why? It's because the two tensions are equal in magnitude. But one is directed against the displacement, because A is sliding down, and the other is directed along the displacement. So you can say that the work done by the tensions goes away when you take A plus B. You could do A on B separately, and then you could sum the two equations, and you would find that the work done by the tension goes away. So it's better to take A plus B in that case. So we might have to go back because they ask us the value of the tension at the end. So we're going to have to look back at A and B separately at the end, but looking at B only, for instance, because B is pretty easy. What is the initial kinetic energy?
0.
0, because we start from rest. What is the final kinetic energy?
1/2 mA plus mB squared.
1/2 MA dA squared plus 1/2 MB dB squared. How do VA and VB compare? Why are they the same? right? Because you have a connection via the rope and you don't have any weird setup with the pulleys. So any displacement of S gives you the same displacement for A. For any displacement for B gives you the same displacement for A. So we get this. And this is equal to the network. So what's doing work when you look at A plus B together? So the weight, what is the work done by WA?
The component.
So remember what we said? It's going to be mg times the delta y. So the delta y that you get here is this. So we know this angle, 60 degrees. So this angle then is going to be 30 degrees. So what is the component along the vertical? It's going to be 2 cosine 30. So the work done by A is MAG cosine 30 times 2. So let's continue here. What's the work done by W?
Just the weight times 2 meters.
Right, so here it's going to be minus MEG 2. What's the work done by the friction force?
What's the friction times 2 meters?
It's going to be the force of friction times 2. And it is negative because it goes against the displacement. So you see that we can get the velocity from here if we know the friction force. So how do you get the friction force? Right? So it's going to be mu times the normal. And what is the normal?
The sine of 30 times
Right.
times 30.
Or the cosine of 60, but that's what we have. So from this you can get the velocity. Yes, Brian?
Doesn't the hanging rate add to the friction force since a certain component of that tension acts towards, oh no, you know it doesn't. Never mind. Sorry, it's.
Oh,
parallel
you were
to-
thinking that maybe the tension was pushing down,
Yeah, I didn't recognize.
and then the normal would have been, but you see it's, the tension is horizontal, I mean along the incline. So from that you can get the velocity. How would you get the tension force after that?
Tension is equal to the mass of B times gravity.
Oh, can I say that?
Or WB.
Can I say that I have the tension B is equal to WB?
No, because it's moving.
Because it is accelerating, yes. So don't say that. I see that sometimes in exams. So make sure you don't say that here.
But you can't say that. TB minus
You cannot say that.
WB equals MA.
So you will have to take the acceleration,
You could really AA to AB with the rope.
right? But is it necessary to do all of this? Is there a way to
No,
find the
you can use
tension
work.
directly?
You just use work because instead of taking the component of work from weight, you can take A as an isolated system and then factor in the work done by the tension, which would be the work of
Right.
tension times 2 meters.
You could even take B only, because it's the same tension and B doesn't have as many forces. You see, if you do it for B only, you will get 1/2 m VB squared